Good morning to all of you. I am Dr. Rama Krishna from KL University, delivering series of lectures on the course heat transfer. The other day, we had a discussion on heat exchangers, preliminary part, where the logarithmic mean temperature difference method elaborately we have discussed. And today's session is to deal with the number of transfer units or effectiveness method, and at the end of this session the student will be able to understand what is effectiveness of a heat exchanger and how to find effectiveness of heat exchanger, and what is the significance of number of transfer units method in the design of heat exchangers, and how to develop relationship for effectiveness, number of transfer units, and the heat capacity ratio, and how to analyze heat exchangers when outlet temperatures of both the fluids are not known using this effectiveness and NTU method, and how to apply NTU method in the design of heat exchangers. So before going to today's class, I feel in the last class I had rushed through the heat exchangers part 1 relatively at a faster rate, because the part 1 heat exchanger majorly deals with energy balancing only. The heat lost by the hot fluid is equal to heat gained by the cold fluid, and we have derived one more expression for logarithmic mean temperature difference. So across the hot fluid and cold fluid, another equation is developed, which we have seen in the convective combined conduction and convective transfer of the fundamental chapter, depending on overall heat transfer coefficient. So Q is equal to UA LMTD. So the earlier topic centered around three equations. One is Q equal to MHCH THI minus THO, and the other one is MCCC TCO minus TCI. The first equation is to determine the heat lost by the hot fluid when its temperature drops from THI to THO. And the second equation is the heat gained by the cold fluid when the cold fluid temperature increases from TC inlet to TC outlet, TCO. Under adiabatic conditions, the heat lost by hot fluid is equal to heat gained by the cold fluid. So we have developed two equations, Q equal to MHCH THI minus THO, which is also equal to MCCC TCO minus TCI. This is as a bulk, what is the heat lost by the hot fluid and what is the heat gained by the cold fluid. In addition to these two, we have another equation where the heat exchange takes place between hot fluid and cold fluid by means of combined conduction and convection mode, and the effective temperature difference between the two fluids. We have derived an expression and found that it is logarithmic mean temperature difference. Hence, based on that, the third equation is Q equal to UA LMTD, logarithmic mean temperature difference. Whether it is parallel flow or counter flow heat exchanger, I repeat, the logarithmic mean temperature difference is delta T inlet minus delta T outlet by logarithm of delta T inlet by delta T outlet. To determine the delta T at inlet and delta T at outlet, you have to first draw how the temperature is varying along the length of the heat exchanger. Identify in parallel flow or in counter flow what is the temperature difference between the two fluids at inlet and at the outlet. You can calculate LMTD. If it is a cross flow heat exchanger or 2 shell 4 pass heat exchanger, or 1 shell 2 pass heat exchanger, or 1 fluid mixed and other fluid unmixed. Different varieties of heat exchangers are there. For all those things you have to apply a correction factor. The LMTD counterflow you have to multiply with that correction factor. So hence 3 equations are there to determine the heat transfer in a heat exchanger where 2 fluids are exchanging heat between them. So one is MHCH THI minus THO, other one is MCCC TCO minus TCI, and the third one is UA LMTD. This LMTD depends on THI, THO, TCO, TCI. 3 equations are there. Hence, using these 3 equations, you can determine 3 unknowns. Maybe Q, one unknown, THO, another unknown, area of the heat exchanger, third unknown. That means TCO, TCI are given, THI is given, mass flow rates are given, overall heat transfer coefficient is given. So we know 3 temperatures, mass flow rates and overall heat transfer coefficient. You have to determine the 4th temperature, rate of heat transfer and area. So first thing is, because we don't TCO, TCI, apply the equation MCCC TCO minus TCI, you will get the Q. One unknown is solved. The same Q is MHCH THI minus THO. So we know Q, we know THI and mass flow rates, you determine THO. Second unknown is also found. Now using these 4 temperatures, you determine LMTD, and Q is also equal to UA LMTD because we know overall transfer coefficient. From this we can determine the area of the heat exchanger required. That is what we do in general in the logarithmic mean temperature difference method of designing a heat exchanger. The common observation is we have 3 equations, so we can determine 3 unknowns. Now take a special case where you know U, you know A also, and you know the mass flow rates, MHCH, MCCC, heat capacities. You know THI, inlet temperature of hot fluid, and you know inlet temperature of cold fluid. You are asked to determine the rate of heat transfer Q, outlet temperature of both fluids THO, TCO. Again, 3 unknowns are there, Q, THO, TCO. 3 equations are there. So we should be able to solve. But the first equation, we don't know THO, so we cannot solve this. And we don't know Q. 2 unknowns are there. In the second equation, Q equal to MCCC TCO minus TCI, again we don't know Q and we don't know TCO. Again 2 unknowns are there, so we can't solve the second equation. In the third equation, Q equal to UA LMTD, of course Q we don't know, UA are known, but LMTD depends on these temperatures. Because we don't know the temperatures, we cannot determine LMTD. So therefore, the solution of the problem becomes difficult. So if the fluid inlet temperatures, fluid mass flow rates, type and size of heat exchanger are given, and you are asked to determine the heat transfer rate, outlet temperatures of hot and cold streams. 3 unknowns, 3 equations, but the solution is difficult. One way is you assume THO, some value, then calculate Q, equate that Q and find TCO. Now you know THO, TCO, THI, LMTD, find out, and then find UA LMTD, again find Q, this Q and this Q both are same, then your THO assumption is correct. Otherwise, change THO. So you have to go on assuming the values of THO or TCO, and then you have to repeat until the answer converges with your assumption. Number of iterations are required. It is a cumbersome process, not advisable. So that leads to development of another method instead of LMTD method. It is effectiveness NTU method. So we follow effectiveness NTU approach to determine or to design a heat exchanger when both outlet temperatures are unknown. So before going to that method, let us see what is effectiveness of heat exchanger and what is this number of transfer units. Then we will identify how best I can use this effectiveness and NTU method to determine the unknown parameters in the design of heat exchanger. Let us start with effectiveness. The effectiveness of a heat exchanger is defined as the ratio of actual heat transfer rate divided by maximum possible heat transfer rate that could happen in ideal condition. Actual heat transfer rate Q equal to MHCH THIO minus THI minus THO or MCCC TCO minus TCI. This is the actual heat transfer rate. And the second one is maximum possible. So if maximum heat exchange takes place, ideal condition, what would be the rate of heat transfer? That ratio Q by Q maximum is defined as effectiveness epsilon. And now actual heat transfer rate, we know Q equal to MCCC TCO minus TC in or MHCH TH in minus TH out, where this CC and CH are called heat capacities of fluids. Capital CH is the product of mass flow rate of hot fluid and the heat capacity of hot fluid. So heat capacity of the cold fluid, CH, is mass flow rate of hot fluid into specific heat of hot fluid. Similarly, heat capacity of cold fluid is mass flow rate of cold fluid into specific heat of cold fluid. This is called capital CH and this is capital CC, known as heat capacity. So you can write the equation for actual heat transfer rate as heat capacity of cold fluid, that is MCCC into TCO minus TC in or MHCH into TH in minus TH out. And the maximum temperature difference you can achieve is when you take the temperature difference between inlet hot fluid temperature minus inlet cold fluid temperature difference. That is always because the highest temperature is hot fluid inlet temperature. The lowest temperature in the heat exchanger is cold fluid inlet temperature. So that difference is the delta T maximum. Now let us see case by case. Let us assume the cold fluid enters at TC in, and if maximum heat transfer occurs between the fluids, it can come out TCO equal to THI. See the dotted line. The cold fluid enters at TCI. Normally it goes like this. May not be able to reach the THI. Suppose maximum heat transfer occurs. This TCI can go up to TCO. Now delta T maximum is TH in minus TC in. You understand? Therefore, we can say that under such circumstances, the heat lost by hot fluid is nothing but heat gained by the cold fluid. That is, the heat gained by the cold fluid is MCCC TCO minus TCI, which is equal to MCCC. This TCO is also equal to THI minus TCI. And if you look at the temperature difference, the THI minus THO, that is, the temperature drop in hot fluid is small, whereas temperature gain by the cold fluid, this difference, TCI and TCO difference, is more. So THI minus THO is less than TCO minus TCI. We know the fundamental energy balance equation, Q equal to MHCH delta T of hot fluid equal to MCCC delta T of cold fluid. The delta T of hot fluid is small and delta T of cold fluid is large. And MHCH is heat capacity of hot fluid, MCCC is the heat capacity of cold fluid. Kindly pay a little more attention here. Heat capacity of hot fluid into delta T of hot fluid is equal to heat capacity of cold fluid into delta T of cold fluid, energy balance equation. Delta T of hot fluid is less than delta T of cold fluid, obvious from this figure. Because delta T of hot fluid is small, to make this product equal, the MHCH should be a higher value and MCCC should be a lower value. Hence, we can say that the CH, heat capacity of hot fluid, is greater than heat capacity of cold fluid. Catch the point here. The hot fluid is subjected to low temperature difference. Cold fluid is subjected to high temperature difference. The product should be equal. Lever rule means the heat capacity of hot fluid should be greater than the heat capacity of cold fluid. Hence, CH must be greater than CC. Then we can write the formula MCCC THI minus TCI, where MCCC is the heat capacity of cold fluid, which is less than heat capacity of hot fluid. Hence, it is known as minimum heat capacity fluid. So we write C minimum into THI minus TCI. So therefore, the formula for maximum possible heat transfer in a heat exchanger is minimum heat capacity fluid into THI minus TCI. I will repeat. Look at this figure. The cold fluid is undergoing maximum temperature rise. So I am assuming that maximum heat transfer is occurring in cold fluid. So the formula for Q maximum is MCCC into TCO minus TCI. This TCO, because it is undergoing maximum temperature rise, is equal to THI. So therefore, Q maximum is equal to MCCC into THI minus TCI. Look here, Q maximum is MCCC into THI minus TCI. And what is this MCCC? Heat capacity of cold fluid. And what is MHCH? Heat capacity of hot fluid. In this figure, if you write the energy balance equation, you will identify that the minimum heat capacity fluid is cold fluid because it is subjected to maximum temperature difference. So we can conclude like this. From this equation, by applying lever rule, you can say if delta T of hot fluid is low, MHCH should be high. If delta T of cold fluid is low, MC should be higher than MHCH. Otherwise, this equation will not satisfy. So, you can say that the fluid which is subjected to, I will repeat, the fluid which is subjected to maximum temperature difference is minimum heat capacity fluid. It's a very important statement. Please remember, the fluid which is subjected to maximum temperature difference is the one which is of minimum heat capacity fluid. So therefore, I can write the equation for effectiveness Q actual by Q maximum as MHCH THI minus THO or MCCC TCO minus TCI divided by Q maximum as C minimum into THI minus TCI. So what is the formula we have obtained for Q maximum? C minimum into THI minus TCI. If C minimum in this case is MHCH or MCCC, in the case 1 we have taken, C minimum is, which is C minimum? MCCC. Therefore, it is better to choose in the numerator this equation, MCCC TCO minus TCI. So this MCCC C minimum cancels and effectiveness is TCO minus TCI by THI minus TCI. You understand? But anyhow, what is the guarantee that the cold fluid is subjected to maximum temperature rise? Why only I have to consider this way? Why not the other way? Go to the second case. Now in the second case, let us assume the cold fluid is getting heated up from TCI to TCO normally, but the hot fluid is entering at THI subjected to maximum temperature drop and leaving at TCI like this. This is from TCI to TCO as usual, but hot fluid which is entering at THI is subjected to the maximum temperature drop and leaving at TCA, which is equal to THO. Now again, if you write Q equal to MHCH delta T hot and MCCC delta T cold, from this figure you can observe that the temperature rise of cold fluid is from TCI to TCO, very small, whereas the temperature drop of hot fluid is THI to TCI is large. So delta T of hot fluid is larger than delta T of cold fluid. Hence, because delta T of hot fluid is high, the heat capacity of the hot fluid will be minimum heat capacity. You can also write this as Q equal to CH delta T hot equal to C. So to satisfy this equation, the minimum heat capacity fluid should be MHCH or hot fluid. So that is what I said. The fluid which is subjected to maximum temperature difference is that having minimum heat capacity or C minimum fluid. Now maximum heat transfer is equal to Q maximum is equal to C minimum into inlet temperature of both fluids. So in this case also MHCH into THI minus TCI, where MHCH is C minimum. So the formula for Q maximum is a general formula, C minimum into inlet temperature of both the fluids, that is maximum delta T maximum. So Q maximum is equal to C minimum into THI minus TCI. In this case, MHCH into THI minus TCI. Therefore, effectiveness is again Q actual by Q maximum, etc. What is C minimum in the second case? MHCH. So if you substitute MHCH here and use the first one, MHCH into THI minus THO in the numerator, MHCH, MHCH cancels, and you will get the effectiveness formula as THI minus THO by THI minus TCA. Carefully observe, in the effectiveness formula only 3 temperatures are involved, either THI, TCI and THO, or THI, TCI and TCO. So 3 temperatures are involved in effectiveness. We know THI, TCI, inlet temperatures, and if you know effectiveness, you can determine the third temperature. Once you know the third temperature, using the fundamental equations Q equal to MHCH delta TH equal to MCCC delta TC, you can determine the fourth temperature. Once fourth temperature is known, LMTD you can determine area, etc. You can go back to that method. So the objective of this effectiveness NTU method is first to determine the So there are how to identify the minimum heat capacity fluid. 2 steps. First one, find out MHCH, because you know the mass flow rate of hot fluid and you know the mass flow rate of cold fluid, and you know the specific heat of hot fluid and you know the specific heat of cold fluid. So find out MHCH and find out MCCC. Whichever is minimum value, that is called minimum heat capacity fluid. That is first step, direct method. The second method is from the temperature differences. If all the 4 temperatures are known, imagine the one which is subjected to maximum delta T is minimum heat capacity fluid. That is second way to identify minimum heat capacity. So once you identify the minimum heat capacity fluid, you can then, in the place of C minimum, you can then use either MHCH or MCCC. Depending on this C minimum, it is better to choose in the numerator either MHCH delta TH or MCCC delta TC, so that very easily you can determine unknown temperatures. Next term in this method is number of transfer units. Number of transfer units is a dimensionless quantity. It is given by the formula UA by C minimum. We will come to that. Whereas C minimum is minimum heat capacity fluid, U is the overall heat transfer coefficient, and A is the area. If you write the units of it, you will get no units. So hence NTU signifies the number of units of heat exchange between hot fluid and cold fluid, or between these two fluids. How many units of heat? Let us not worry what is the dimension or what is the quantity. It is only a number, maybe 2 or 0.7 or 1.5 or 3. NTU 2 means 2 units of heat exchange occurred between hot fluid and cold fluid in that particular heat exchanger with the flow rates. Therefore, NTU signifies the number of units of heat exchange, that is, that 1 unit could be 100 watts, or 1 unit could be 300 watts, or 1 unit could be 2 kilowatts. It is immaterial, we are not sure. It varies, but so many units of heat exchange takes place between hot fluid and cold fluid is a permanent or the constant thing for the given heat exchanger, as long as the flow rates are same. So NTU is UA by C minimum, where C minimum is minimum heat capacity, which is nothing but the product of mass flow rate and specific heat of the fluid. It is a non-dimensional thermal size of the heat exchanger and heat transfer unit heat capacity of the fluid for specified values of C minimum and U. NTU measures the heat transfer surface area. Larger the number of transfer units means larger the heat exchanger, because NTU, UA by C minimum, is NTU is high means area is also high. And we define in this case the heat capacity ratio C is equal to C minimum by C max. Now it is established that the effectiveness of a heat exchanger fairly depends on the heat capacity ratio and number of transfer units. That is the logic. Now we have to develop expressions for effectiveness of a heat exchanger in terms of its heat capacity ratio and number of transfer units. You understand now? First, you identify whether MHCH or MCCC. Now let us see how to establish the relationship between the effectiveness of a heat exchanger as well as the heat capacity ratio and number of transfer units. Consider parallel flow heat exchanger. Effectiveness is defined as Q by Q maximum. And we know the heat capacity of hot fluid is MHCpH and heat capacity of cold fluid is MCCpC. And Q is nothing but effectiveness into Q maximum, and maximum possible heat transfer is always equal to minimum heat capacity fluid into THI minus TCI. And this equation we have derived already in the LMTD derivation of parallel flow heat exchanger, which I have picked up from there. Logarithm of delta T outlet by delta T inlet is equal to minus UA 1 by MHCH plus 1 by MCCC. So this MHCH is written as capital CH and this MCCC is written as capital CC, and then bring out CC outside. You will get UA by CC into CC by CH plus 1. And we know that Q equal to MCCC, that is heat capacity of cold fluid into temperature drop of cold fluid, which is also equal to heat capacity of hot fluid into temperature rise of hot fluid. So from this equation, forgetting that Q value, you can write THO is equal to you take the CH to this side, CC by CH into TCO minus TC in, and this minus sign is taken here, and TH in. So THO is THI minus CC by CH into TCO minus TCI. We will substitute that in the place of THO here. So I have eliminated that temperature THO, outlet temperature. One outlet temperature I have eliminated. That is what I am doing ultimately. I am substituting the temperatures, outlet temperatures in the known values in terms of by CH plus 1. That is elaborately written, and we will have logarithm of THI minus TCI plus TCI minus of CC by CH into TCO minus TCI minus TCO by THI minus TCI is equal to minus UA by CC into CC by CH plus 1. what we will do is, we got THI minus TCI and THI minus TCI. Separate it. You will get 1 minus of, and in this take out the common TCI term and TCO term also. You will get 1 plus CC by CH into TCO minus TCI by THI minus TCI, which is equal to the right hand term. And the effectiveness is CC into TCO minus TC by C minimum into THI minus TC. I am assuming here minimum heat capacity fluid is cold fluid, MCCC. So TCO minus TCI by THI minus TCI is equal to effectiveness into this CC by C minimum. When it goes to the left hand side, becomes C minimum by CC. So let us substitute that. Logarithm of 1 minus 1 plus CC by CH, and in this place I have taken out common TCO minus TCI by THI minus TCI as effectiveness into C minimum by CC equal to minus UA by CC 1 plus CC by CH. I am assuming C minimum as CC, so CH by CC by CH is C minimum by C maximum, and this is also C minimum, and the CC is C minimum cancels out. You will get effectiveness is equal to 1 minus e to the power minus UA by CC 1 plus CC by CH divided by 1 plus CC by CH into C minimum by CC. This C minimum by CC becomes 1. You get the expression effectiveness is 1 minus e power minus UA by CC is C minimum 1 plus C minimum by C maximum plus 1 minus e power minus n becomes 0. So you will get 1 by 1 plus c. If c is equal to 1, then you put c equal to 1 in this. Effectiveness is 1 minus e power minus 1 plus 1, 2n minus 2n by 1 plus 1, 2. So these are all different cases where you have to carefully apply the formula for effectiveness and then check. Now let us have a quick look at the derivation of effectiveness as a function of heat capacity ratio and number of transfer units for a counterflow arrangement. I am going to the beginning now for the clarity of viewers. Take dH minus Tc derivative, dTH minus dTc. And we know dQ is minus CH dH minus CC dC. In counterflow, temperature of hot fluid drops and temperature of cold fluid also drops in the direction of positive X. So we write d of TH minus Tc is in the form of dQ as dQ by MHCH, dQ by MCCC, which is equal to U dA TH minus Tc into 1 by Cc minus 1 by CH. Now integrate on both sides by bringing TH minus Tc to the left hand side. The inlet temperature difference is THI minus TCO. The outlet temperature difference is THO minus TCI. So the integration is temperature difference at inlet to temperature difference at outlet. Derivative of TH minus Tc by TH minus Tc equal to minus U 1 by Cc plus 1 by Ch integral 0 to a dA. This is actually. And from the definition of effectiveness, minus is taken out, both are minus, so it becomes plus here. Effectiveness is again CH by THI minus THO C minimum, same. Either it is CH or CC. General formula we have written. In the denominator, it is minimum heat capacity fluid into temperature difference of both the fluids. So from this definition, you can write THO as a function of effectiveness like this, or you can write TCO as in terms of effectiveness like this. So we are eliminating THO and TCO by substituting effectiveness value in that. Now we will write this THI minus, this is a TCO. When you substitute logarithmic term here, you will get logarithm of TH minus sign is there, so it becomes logarithm of THI minus TCO by THO minus TCI. So in the place of TCO, I am substituting this term. So THI minus TCI plus C minimum by CC into this. Similarly, in the place of THO here, I am substituting this THI minus C minimum by CH into this. Because it is a logarithm, the logarithm is removed and it goes to the other side, it becomes e power minus UA 1 by CC plus 1 by CH. So that is again elaborately written by bringing out the TCA to the outside, and this is the expression which you will get, THI minus TCI, and this is THI minus TCI, the rest is common, e power minus UA, etc. Now 1 minus C minimum by CC into effectiveness, and this is 1 minus C minimum by CH into effectiveness is e power minus UA into 1 by CC minus CH. That is 1 minus C minimum by CC into effectiveness is equal to e power minus UA into 1 by CC minus 1 by CH and multiplication with this. So elaborate and bring effectiveness terms to one side and other terms to the other side, and let minimum heat capacity fluid is CC, C minimum is cold fluid, then you will get the effectiveness expression as 1 minus e power minus UA by CC into 1 minus CC by CH by C minimum by CC minus, that is 1 is taken out, minus CC by CH into e power minus UA by CC, etc. So this is equal to effectiveness is 1 minus e power minus UA by the same thing, and this is equal to 1 minus e power minus UA by C minimum, 1 minus C minimum by C maximum, and again C minimum by C maximum, 1 minus C minimum by CH, e power minus UA by C minimum, etc., etc. So this results in effectiveness is equal to 1 minus e power minus n into 1 minus C by 1 minus C into e power minus n into 1 minus C. This is C minimum by CC, it gets cancelled here 1. This is C minimum only. Because we are assuming CC as C minimum, this C minimum and CC, C minimum gets cancelled. You will get 1 minus e power minus n into 1 minus C by 1 minus C minimum by C maximum is C into e power minus n into 1 minus C. This is the expression for effectiveness of a counterflow heat exchanger. Anyhow, students are advised to take care of signs which I might have missed somewhere here and there. Take care of those signs, and this is the procedure to derive the expression for effectiveness of a counterflow heat exchanger. Now let us see. This expression, if you see, 1 minus e power minus n into 1 minus c by 1 minus c into e power minus n into 1 minus c. The c is heat capacity ratio, C minimum by C maximum. N is the number of transfer units. Suppose C is equal to 0. Imagine. That is, heat capacity ratio is 0. Then you will get 1 minus e power minus n, that's all. The denominator becomes 1. Suppose C is equal to 1. When C is equal to 1, in this equation if you substitute C equal to 1, it becomes 1 minus 1, 0 by 1 minus 1, 0, indeterminate. So therefore you have to apply the L'Hospital rule and differentiate both numerator and denominator separately with respect to C, and then substitute 1. So that differentiation I have shown here. Differentiation of 1 is 0, and the differentiation of minus e power minus n into 1 minus c is given here. And similarly here you have one differentiation is 0, minus c is taken out, and the second term consists of c and e power minus n into 1 minus c. UV rule you have to apply, and elaborately that differentiation is done. And now substitute c equal to 1, you will get effectiveness is equal to n by n plus 1. This is the general formula for effectiveness of a heat exchanger when C equal to 1, which you can also write it as 1 by 1 plus 1 by n. Suppose n tends to infinity. Suppose n tends to infinity. Then it results in effectiveness is equal to 1. Because 1 by infinity is 0, effectiveness is 1. When C is equal to 1, in case of parallel flow heat exchanger, effectiveness formula is 1 minus e power minus n by 2. And when C is equal to 1 and n tends to infinity, you will get effectiveness of a parallel flow heat exchanger as 1 by 2, that is 0.5. See here. Therefore, the maximum possible effectiveness in case of counterflow heat exchanger is 100%. Whereas for a parallel flow, the maximum effectiveness is only 50%. So that is the reason why almost all heat exchangers are designed for counterflow arrangement, where there is more possibility for the cold fluid to absorb the heat, or hot fluid which can be subjected to maximum temperature drop. If C is equal to 0, like C equal to 1 we have analyzed, when C equal to 0, this effectiveness formula becomes 1 minus e power minus n for counterflow. Even for parallel flow also, it is 1 minus e power minus n. That means it is same for both parallel flow and counterflow. Normally C equal to 0 only when one of the fluid is condensing or evaporating. And we have already seen that when one of the fluid is condensing or evaporating, the direction of flow of fluids are immaterial. Whether it is parallel, counter or cross flow, the effectiveness remains same. So we have only seen for parallel flow and counter flow like this, 1 minus e power minus n into 1 plus c by 1 plus c, and for counter flow effectiveness 1 minus NTU into 1 minus c by 1 minus c into e power minus n into 1 minus c. And there are other types of heat exchangers for which the formulas for effectiveness are given here. But anyhow, these are available in the form of equations as well as graphical form also. For example, for parallel flow heat exchanger, if you know the C minimum by C maximum and the number of transfer units UA by C minimum, you can determine effectiveness from this graph. And this is for counter flow. And this is for one shell 2, 4, 6 tube passes, and this is for 2 shell 4, 6, 4, 8, 12 tube passes, and this is cross flow, both fluids unmixed, and this is cross flow, one fluid mixed and other unmixed. So normally if you look at this graph, the number of transfer units versus effectiveness, for counter flow the effectiveness is highest, and then cross flow with both fluids unmixed is intermediate, and the least is in case of parallel flow. And the effectiveness versus N, if you again see, for those fluids having C equal to 0, it takes the curve like this, like in condenser and boiler. If C is equal to 1, that means effectiveness becomes the lowest value. So now, nutshell, what we have seen from the effectiveness and NTU relations. Effectiveness ranges from 0 to 1. It increases rapidly with NTU for small values, that is roughly up to 1.5, but thereafter slowly for larger values. The slope decreases. You might have observed this graph if you see like this. Up to 1.5 rapidly increases, and afterwards the slope falls down. High effectiveness is desirable from heat transfer point of view, but undesirable from economic point of view, because NTU greater than 3, it requires large area, hence it is not justified. For a given value of NTU and C, the counterflow heat exchanger has got highest effectiveness, followed by cross flow, and lowest is for parallel flow. Already we have seen. And effectiveness is independent of capacity ratio for NTU values less than 0.0, and the capacity ratio varies between 0 to 1. C equal to 0, C is already we have seen condenser and boiler. C is equal to 1 is the case where you have the regenerator of a gas turbine power plant or air preheaters, etc. Now let us have a quick look at different problems. Three kgs per second, and water enters at 90 at the flow rate of 1 kg per second. Determine the heat transfer rate and outlet temperatures if you know the overall heat transfer coefficient and the area of the heat exchanger. See, typically only two temperatures are given, inlet temperatures and outlet temperatures of both fluids are unknown. So you can't use directly the equation Q equal to MHCH delta TH, or you cannot use MCCC delta TC, or you cannot use UA equal to LMTD, because in each equation there are two unknowns. So obviously only when two temperatures are given we have to go for effectiveness NTU method. Let us determine heat capacity of cold fluid. The cold fluid is air and hot fluid is water in this problem. So cold fluid heat capacity is MCCC 3015 joule per second. and hot fluid heat capacity MHCH is 4186 joule per second. Therefore, the minimum heat capacity fluid is cold fluid, that is air, and heat capacity ratio C minimum by C maximum is 0.7202. Because we know now UA and C minimum, you can determine the number of transfer units, UA by C minimum 0.995. And this is a parallel flow heat exchanger. Therefore, effectiveness formula for a double pipe parallel flow heat exchanger is 1 minus e power minus n into 1 plus C by 1 plus C. We know the C value, we know the n value. By substituting that, you will get the effectiveness 0.48. And as per the definition, effectiveness is actual heat transfer by maximum possible heat transfer, that is C minimum into THI minus TCI. Here the minimum heat capacity fluid is MCCC. So let us choose the actual heat transfer formula MCCC TCO minus TCI. In the denominator also MCCC THI minus TCI. MCCC cancels. And this effectiveness is now having only 3 temperatures, THI, TCI and TCO. We know the effectiveness, we know THI and we know TCI, only unknown is TCO. By substituting the values, you will get TCO equal to 53.6. Once you know TCO, you can determine Q actual by using the formula MCCC TCO minus TCI. And this is also equal to MHCH into THO minus THI, that result in THO. That is, now suppose if I make this a counterflow arrangement, what will happen? For counterflow arrangement, effectiveness formula is 1 minus e power minus n into 1 minus c by 1 minus c into e power minus n into 1 minus c. The flow rates are not changed, so therefore overall heat transfer coefficient will remain same. The mass flow rates are not changed, the fluids are not changed, therefore C minimum remains same. It is the same heat exchanger, so the area remains same. So in the simulation of a heat exchanger, when you want to simulate it for different other conditions than the existing working condition, the number of transfer units always remains same. That is the importance of number of transfer units. So whether it is parallel flow or counter flow or cross flow, whatever way you try to use that heat exchanger, the number of transfer units remains same as long as the flow rates remains same. They are untouched. Effectiveness is equal to 1 minus e power minus n into 1 minus c by 1 minus c into e power minus n into 1 minus c, which is equal to 0.5342. You can see the effectiveness of parallel flow heat exchanger is 0.48, but the moment you make it counter flow, its effectiveness increases to 0.53. That is why counter flow arrangement is best arrangement. Again, effectiveness is actual heat transfer by maximum possible. In the maximum possible heat transfer, C minimum is MCCC, so it cancels, and you will get again TCO, and you will get TCO value 57.39. Q actual is 112.73, whereas in the parallel flow it is only 101, so better heat transfer rate. From the Q actual, you can determine the value of THO as 63.07 or whatever it may be. See, so parallel flow and counter flow arrangements, the temperatures we can determine by applying the effectiveness NTU method. Let us move to the second problem. A counter flow double pipe heat exchanger is to heat water from 20 to 80. Both temperatures are given. Heating is to be accomplished by geothermal water available at 160. The inner tube thin wall diameter 1.5, overall heat transfer coefficient is given. Determine the length of heat exchanger required to achieve desired heating. So actually area we have to determine. So this is a counter flow heat exchanger. Cold water and hot water, they are flowing in opposite direction to one another. The heat capacity of hot fluid is mH into Cph, 8.62 kilowatt per degree centigrade, and heat capacity of cold fluid is only 5.02. So C minimum is MCCC and C maximum is MHCH. So C heat capacity ratio is 0.583 and maximum possible heat transfer rate is C minimum into the 702.8. Now the actual heat transfer is given by the formula MCP T out minus T in of water, because both temperatures are given, you get 301 kilowatts, and effectiveness is Q by Q maximum 0.428. Knowing the effectiveness, you can determine the NTU by using the relation effectiveness is 1 minus e power minus n into 1 minus c by 1 minus c into e power minus n into 1 minus c, that is transformed to give the value of NTU. You will get 0.651, and NTU is UA by C minimum. Therefore, area is 5.11 meters square, which is equal to pi dl. So therefore, you will get length of the heat exchanger 108 meters. Purposefully, this problem is solved using number of transfer units method. You can also use it by using LMTD also, because we know all the two temperatures and the flow rates. You can determine directly Q. From the Q, you can determine TCO. You can determine LMTD. From there, UA LMTD, you will get the area, and you can solve the length of the tube is area by pi d 108 meters. But this is an illustration how NTU method is also useful to determine the area of a heat exchanger, etc. Third problem. Hot oil is to be cooled by water in 1 shell pass and 8 tube pass. 1 shell and 8 tube pass heat exchanger. The tubes are thin walled and made up of copper, internal diameter 1.4. Length of the pass in each heat exchanger is 5 meters, and overall heat transfer coefficient is 310. Water flows to the tube at 0.2 kg per second, and oil is in the shell. The inlet temperature of water and oil are given, outlet temperatures both are unknown. You are asked to determine Q. So general problem, general method we cannot solve. We have to go for effectiveness NTU method. This is the configuration shown, of course. And now CH, heat capacity of hot fluid is 0.639. I'm sorry, one is heat capacity of hot fluid. That 0.3 kg per second is oil, is heat capacity CH, and the other one is CC 0.8. So 0.1 kilowatts, and the surface area is n into pi dl. You will get 1.76 meters square, and number of transfer units is 0.853. The expression for this type of heat exchange is given in the literature. You can pick it up, or from the table which I have shown here, you will get the effectiveness 0.47. Once you know the effectiveness, actual heat transfer is effectiveness into Q maximum 39.1 kilowatts. So you know Q is MCCP TCO minus TC in. From that you can determine the TC out, which is also equal to MHCH into TH in minus TH out. You can determine the TH out. Therefore, the temperature of cooling water will rise from 20 to 66 as it cools the hot oil from 150 to 88.8 in this heat exchanger. A small correction here is required. Let us go to the last problem. A hot gas at the rate of 16.2 kg per second at 648 degrees centigrade is used to heat 20.2 kg per second of cold fluid from 100 degrees centigrade. Overall heat transfer coefficient area is given. Find the fluid outlet temperatures for counter flow and parallel flow. Again, MHCH, MCCC. Minimum heat capacity fluid is hot fluid. Maximum heat capacity fluid is cold fluid. So C is equal to C minimum by C maximum. You got 0.6702. N, number of transfer units is UA by C minimum, 0.76. You know U, 920, area 43.8, C minimum, that is 57.02 into 10 cube, you will get this. Let us first take parallel flow. Effectiveness formula is 1 minus E power minus N into 1 plus C by 1 plus C, 0.4148. And because C minimum is MHCH, actual heat transfer formula I have chosen MHCH into THI minus THO. So MHCH, C minimum cancels. You will get effectiveness THO equal to 420.68. Unknown is THO, effectiveness is already known. We'll get it. And once you know THO, you can calculate TCO by using effectiveness is now MCCC TCO minus TCI by C minimum into M. MCCC is C maximum. Bring that MCCC to the denominator, you will get C minimum by C maximum. C minimum by C maximum is C, 0.6702. So 1 by 0.6702 into TCO minus all the three temperatures are known, TCI, THI, TCI, other two temperatures. You will get the value of TCO as 252.3. Now for counterflow arrangement, effectiveness is 1 minus E power minus N into 1 minus C by 1 minus C into E power minus N into 1 minus C. That is equal to 0.443. Hence, by substituting again minimum heat capacity fluid as MHCH, you will get THO as 405, and also using the same way MCCC TCO minus TCI by C minimum into THI minus TCI, and bringing MCCC C maximum into the denominator, you will get C minimum by C maximum in the denominator, that is C, 0.6702, you will get TCO value. So that is how the problems on heat exchanger we have to solve. Sometimes remember, the four temperatures will be given and you will be asked to determine the effectiveness of heat exchanger. That is possible. That kind of problems I have not taken up here. Inlet temperature and outlet temperature of both the fluids are given and you are asked to determine effectiveness of heat exchanger. That is the objectivity. Carefully follow. Now find out the delta T of cold fluid and delta T of hot fluid. Suppose delta T of cold fluid is more than delta T of hot fluid. So, because delta T of cold fluid is more, the minimum heat capacity fluid is the one which is subjected to maximum delta T. Hence, MCCC will become C minimum. That is how you have to identify. Then go to the formula effectiveness equal to, in the denominator, in the place of C minimum, you choose MCCC. So automatically in the numerator also you have to choose MCCC. MCCC cancels. You will get effectiveness in terms of three temperatures. All the four temperatures are given. You can determine the effectiveness. That problems I have not taken up. Maybe in most of the competitive examinations, such type of questions are asked for 1 or 2 marks, etc. Now let us quickly have a look at what we have learned till in the heat exchanger chapter. Heat exchanger is a device used for effective heat exchange of heat energy between two fluids, a hot fluid and cold fluid. Depending on the direction of flow, they are classified as parallel flow, counter flow or cross flow. The performance analysis of heat exchanger is done by using three fundamental equations. Q equal to MCCC TCO minus TCI, which is equal to MHCH THI minus THO, which is also equal to UA LMTD, where U0 is overall heat transfer coefficient based on outside area A0, and this, to determine this U0 we have to use the equation R total is equal to 1 by U0 A0 equal to 1 by HII plus fouling resistance inside plus conduction wall resistance of the pipe material plus fouling resistance outside plus 1 by H0 A0. This RFI and RF0 are called inside and outside fouling resistance caused due to the tube surface covered by scale, dirt, soot and deposit of ash, etc., etc., depending on its application. LMTD for parallel flow or counter flow, the general equation is delta T inlet minus delta T outlet by logarithm of delta T inlet by delta T outlet. Only you can identify the delta T inlet and delta T outlet if you draw the figure, length of the heat exchanger versus temperature. In case of cross flow or multi-pass heat exchangers, the LMTD equation is LMTD is equal to correction factor into LMTD counter flow, where correction factor we can obtain from different figures or graphs depicted in the data books. Effectiveness of a heat exchanger is defined as the ratio of actual heat transfer to that of maximum possible heat transfer. And maximum possible heat transfer is always given by the formula C minimum into THI minus TCI. And number of transfer units is given by UA by C minimum. It is a dimensionless number. Effectiveness method of heat exchanger is nothing but predicting the performance and outlet temperatures of existing heat exchanger for different inlet conditions or different mass flow rate conditions. Formulas for a different effectiveness as a function of heat capacity ratio and N are presented in a tabular form in the last discussion we had, as well as in graphical form also. Effectiveness is given as a function of heat capacity ratio and number of transfer units. So in case of design of heat exchanger, we have to concentrate more on maximizing the transfer rate, minimizing the pumping power or pressure drop, and minimizing the cost of the equipment, minimization of size and weight, and what kind and what type of heat exchanger we have to choose, and what are the different materials we have to select for the tubing or for the shell, etc. These are the design considerations in the selection of a heat exchanger. Let us have a quick look at the questions raised in the last session with reference to the heat exchanger. A compact heat exchanger is only when the ratio of the heat transfer surface to volume exceeds 700 meters square. Therefore, a double pipe heat exchanger cannot be called as a compact heat exchanger. Next, in counterflow heat exchangers, hot and cold fluids move parallel to each other, but both enter the heat exchanger in opposite ends and flow in the opposite direction. In cross-flow heat exchangers, they move perpendicularly one to the other. The cross-flow is said to be unmixed when the plate force the fluid to flow through a particular interfin spacing and prevent it from moving in the transverse direction. When the fluid is free to move in any direction in transverse manner, then it is called mixed flow. Otherwise, it is called unmixed flow. The heat transfer mode is first from hot fluid to the wall by means of convection and through the wall by conduction, and again from wall to the cold fluid by means of convection. So it is a best example for combined conduction and convection problem. Whenever the thickness of the next question is, answer to the next question is, if the thickness of the tube wall is small and thermal conductivity of the tube material is high, usually that is the case in any heat exchanger, the thermal resistance of the tube is negligible. HI and H0 need not be same. They depend on the flow rates of fluid and the properties of the fluid. So it is not appropriate or reasonable to say HI is approximately H0 equal to H. Next. When one of the convective heat transfer coefficient is much smaller than the other, for example, HI is very, very less than H0, then we can say UI is equal to U0 is equal to U is equal to approximately HI. That approximation is valid. But anyhow, in normal case, we will calculate and identify. We don't go for these type of approximations. The most common type of fouling is, if this happens in case of HI is far less than H0, for example, condensation and boiling. The values outside the tube, condensation occurs and the H0 is very high. So overall heat transfer coefficient becomes HI itself. So in such case, even though the data is not given with reference to the determining the condensing heat transfer coefficient outside, etc., as an approximation, you can take overall heat transfer coefficient as the inside flowing fluid heat transfer coefficient and proceed. That is the advantage of assuming Ui is equal to U naught is equal to U is approximately equal to HI. Anyhow, next to 54th question. Most common type of fouling is precipitation of solid deposits in a fluid on the heat transfer surface. And another form of fouling is corrosion, chemical fouling. Heat exchangers may also be by the growth of algae in warm fluids. This type of fluid fouling is called biological fouling. It is nothing but an additional resistance to the heat transfer and causes the rate of heat transfer to decrease and pressure drop to increase because the diameter reduces when fouling occurs. So thereby it increases, it offers more resistance for flow. The effect of fouling is represented by a fouling factor RF. Its effect on the heat transfer coefficient is accounted by introducing a thermal resistance RF by AS. The fouling increases with increasing temperature and decreasing velocity. Heat exchangers usually operate for long periods of time with no change in their operating conditions, and then they are modeled as steady flow devices. As such, the mass flow rate of each fluid remain constant, and the fluid properties such as temperature and velocity at any inlet and outlet remain constant. And this is the answer given for that 58th question. And the outer surface of the heat exchanger is assumed to be perfectly insulated, that is the assumption, so that there is no heat loss to the surrounding, and heat transfer thus occurs between these two fluids only. Based on this only, we are able to write the equation Q equal to MHCH delta TH is equal to MCCC delta TC. And the products of mass flow rate and the specific heat is known as heat capacity rate and is expressed as capital C or CC. When heat capacity rates of cold and hot fluids are equal, that is C is equal to 1, the temperature change is same for both the fluids in a heat exchanger. That is, the temperature rise of cold fluid is equal to temperature drop of hot fluid. Then only C will become C minimum by C maximum, that is equal to 1. Heat capacity of infinite for a fluid in a heat exchanger is experienced during phase change process in a condenser or boiler, because delta T tending to 0 during condensation or boiling, when you calculate, it may reach to infinity. The temperature difference between two fluids decrease from delta 1 T1 at inlet to delta 2 at outlet, and arithmetic mean temperature difference is defined as delta T1 plus delta T2 by 2 in case of both the fluids having same heat capacity. The logarithmic mean temperature difference is obtained by tracing the actual temperature profile of the fluids along the heat exchanger, and it is an exact representation of effective temperature difference between hot and cold fluids. It truly reflects the exponential decay of local temperature difference in the flow through pipes. It truly reflects the exponential decay of local temperature difference. Logarithmic mean temperature difference is always less than arithmetic mean temperature difference. When delta T1 is less than delta T2, the ratio must be less than 1, and natural logarithm of such numbers is negative. But the numerator is also negative, denominator is also negative, so altogether the value becomes positive. So therefore, under any circumstance, the LMTD will become negative. In parallel flow heat exchanger, hot and cold fluids enter the heat exchanger at the same end, and the temperature of the hot fluid decreases and temperature of the cold fluid increases. But the temperature of cold fluid can never exceed that of the hot fluid. In case of counterflow heat exchangers, the hot and cold fluids enter the heat exchanger from the opposite ends and hence the outlet temperature of cold fluid may exceed the outlet temperature of hot fluid. The students are advised to draw the figure and then feel how the temperature variation can take place along the length of the heat exchanger. Very simple schematic drawing to experience the answer given for this question number 60. In the LMTD method generally is not useful only when two temperatures are given. Of course, I said you can choose the third temperature, or I mean assume, and then proceed and finally check whether the assumption is correct or not. So a lot of iterations are required. Instead, the effectiveness NTU method is best used. So this is the end of the chapter on heat exchangers, and we have seen some concept questions and we have revised. Fundamentally, heat exchangers chapter is more simpler than any other thing. You have to remember only the basic energy balance equations along with one heat transfer equation UA LMTD. If you cannot calculate LMTD, then you have to go for effectiveness and number of transfer units method, where somehow you have to find the effectiveness, which involves only 3 temperatures. From that, the third temperature can be determined, and so on. It continues. So I request the viewers to go through some of these suggested books by Senjal or Frank Reed or Incropera and David, are written by me for further reading and understanding the course in a more vigorous way. Thank you very much.